Alright, welcome back, guys. So, today we will try to understand this article by Sutton, okay, which was published on March 13 in 2019. The better lesson, okay. Now, if let's read this line by line. I am also trying to understand with you only. I haven't read it till now, so we can learn it together, right? The thing is that it says the biggest lesson that can be read from 70. So we can read the lesson from 70 years of AI research in that is that general methods that leverage computation are ultimately the most effective and by large margin. What does it mean? Okay, so we have to find out, because what does it mean by general methods, right? What does it mean by general methods here, right? Okay, let's go here. Can you explain in brief and in simple language what is general methods here and how they leverage computation? What are we computing here? Okay, so it will tell us. So it says like this: quotes come from Richard Sutton's essay The Better Lesson. It is one of the most important ideas in AI. So the sentence is general methods that leverage computation are ultimately the most effective, right? This means that instead of building AI by hand with lots of human knowledge and rules, okay, so we can define some rules, right? Like, okay, if else conditions, like that. If you have this particular condition, then we have to define a lot of rules, right? According to the human language, it is usually better to build a general learning algorithm and later learn from data by doing its lots of computation. Okay, it's so this part is understandable, right? Like, either we write all the rules which can exist in the world, right? Else we can generalize it with the data, right? We will build a general learning algorithm and later learn from the data by doing lots of computation. Computation is like a different thing. So yeah, what is general methods here? A general method is an algorithm. Okay, that works on many different problems, not just one specific task. Okay, so think of it like this. Human design method is like, suppose you want to compute to recognize caste, right? One approach, it could be cat have pointy ears, like these are the rules, right? You are writing as a human expert, right? Like pointy ears, whiskers, two eyes, a tail, like that. So programmer can manually write all these rules, right? Image, image go through the handwritten rules. Then we can classify it's a cat or not cat, right? So this will work only for cats. Now suppose tomorrow you want to detect dogs, so you have to write the whole new set of rules, right? So this is not general here. General method instead, we use one algorithm, for example a neural network. We don't tell it what cat ears looks like in a what, right? We simply show it cats and dogs images, right? Millions of images, as it is saying. So the algorithm will learn the pattern itself, like what cat look like and how dog look like. So exactly the same algorithm can learn other things like handwriting, speech, language, chess, everything. Only the data changes. This is a general method. Okay, what does leverage computation mean? So it means instead of putting intelligence into a program manually, use lots of computer calculations so the machine can discover the intelligence itself. Right? So what it is saying, instead of putting intelligence into the program, putting intelligence into the program means writing the rules by yourself, right? What we can do, use lots of computer calculations like neural network do during training, right? So the machine can discover the intelligence itself. So machine can identify the patterns itself, right? And the computer keeps doing mathematical operations over and over. For example, suppose a neural network has 100 medial parameters, right? So the training means repeatedly doing the calculations like prediction, error, then update the weights, then predict, then error, then update the weight. This is the computation, right? So millions or even billions of times, that is the computation. So what are we computing here? Mostly we are computing mathematical operations. For example, input is 2, weight is 5, bias is 1. So we multiply input with weight and add the bias. So output will be 11. Suppose the correct answer should have been 10. So what we do? We have error of one digit, one weight, right? So what we do? We update the weight and put it 4.8, and we reduce the error this time, right? And then again we update, make it 4.5. Now we can predict. Computer repeats the correct answer here, right? So computer repeats this process millions or billions of times, right? That repeated optimization is the computation Sutton is talking about, right? For another example, we can talk like in old AI, or you can say human knowledge. Expert wrote rules like protect the king, control the center, knights before bishops, don't trouble pawns, right? So we can program a chess game, but it was a human knowledge, right? It was a general method just. So Alpha Zero knows almost nothing except rules of chess. Then it plays against itself. Game 1, Game 2, 500 million games. After enough computation, it becomes stronger than humans. New human chess strategy was manually programmed. Why is this better? Because human knowledge is limited. A human may think cats have pointy ears, but some cats hide their ears, have unusual poses, are partially occluded. So a learning algorithm discovers many subtle features that humans may never think of write down, right? So the key idea of better lesson was there are two ways to improve AI. Option 1, keep adding smarter human rules. Number 2 is keep increasing data, computing power, or training time. The same learning algorithm keeps improving. So we can increase data, we can increase compute power, we can increase the training time, we can do more computation, right? And history has shown that this approach consistently outperforms handcrafted solutions as compute and data scale. Okay, more data, more computation, same algorithm. It's a better AI for us. Okay, so this is how a brief summary for this single line, right? Okay, let's move forward. What is it? Yeah. The ultimate reason for this is Moore's law, or rather, its generalization of continuous exponential falling cost per unit of computation. Okay, let me understand this also. Right? Um, Can you explain this in brief and simple language? Yeah, this sentence is explaining why general AI methods became so successful over time, right? General AI methods, right? The ultimate reason for this is Moore's law. Okay, let's break it down. What is Moore's law? This is very important for us to understand, right? Moore's law originally said the number of transistors on a computer chip doubles roughly every 2 years. This is Moore's law, guys. Moore's law is number of transistors on a computer chip almost doubles every 2 years, or similarly 18 months also. This was the Moore's law, guys, right? So why we are increasing more transistors? More transistors means more powerful computers. So every few years computers become faster, cheaper and more powerful. What does falling cost per unit of computation mean, right? This is like Moore's law, or rather than generalization continuum. Exponentially falling cost per unit of computation, right? What does it mean? Imagine 20 years ago, suppose performing 1 billion calculations cost 100 rupees, right? Today, because computers are much faster and cheaper, the same 1 billion calculations might cost only 1 rupee for you, right? 2005, 100 rupees, 15, 10 rupees. Now in 25, it is only 1 rupee. So cost per computation keeps decreasing, right? So we can afford to do many more computations for now. Why does this matter for AI? General AI methods like neural network become faster when you give them more data, more training time and more computation. If computation is cheaper, then we can give it more computation for same amount, right? For example, in 2010, computer can do 1 trillion calculations. Today, computer can do 1,000 trillion calculations, right? Now, we can train much larger models like GPT, Gemini, or Cloud, etc. With current computers, right? So algorithm may be similar, but because we can perform vast more computations, it learns much faster, right? What does generalization of Moore's law mean? Others say, or rather, it's generalized because it's not just about transistors count anymore. Even though Moore's law has slowed, the overall cost of computer keeps falling due to many improvements. Like Moore's law has been slowed means like number of transistors may be doubling now in 3 years like this, right? Like not in 18 months, not in 2 years, like we may say 30 months like that, right? So better GPUs are there, better TPUs, better algorithms, better hardware design now, cloud computing, parallel processing. So the broader idea is computing keeps becoming cheaper and more powerful over time, right? So that's also one reason. Let's go ahead. Most AI research has been conducted as if the computation available to the agent were constant, in which case leveraging human knowledge would be one of the only way to improve performance. In the past, I think it is talking about the past, right? Most AI research has been conducted as if the computation available to the agent were constant. Okay, it's not increasing, right? In which case leveraging human knowledge would be one of the only ways to improve performance. But over a slightly longer time than a typical research project, massively more computation inevitably becomes available, right? Seeking an improvement that takes a difference in the shorter term. In which case leveraging human knowledge would be one of the only ways to improve okay performance, but over a slightly longer time than a typical research project. Okay, massively more computation inevitably becomes available. Okay, seeking an improvement that makes a difference in the seeking an improvement that makes a difference in the shorter term. Researchers seek to leverage their human knowledge of the domain, but the only thing that matters in the long run is the leveraging the computation. Hmm. Let me do with here. We will go step by step only, right? Can you explain this in a simple ways and in brief? Right? We don't want long lectures. So this paragraph is one of the main ideas of better lesson. Okay, let's simplify it sentence by sentence. Most AI research has been conducted as if the computation available to the agent were constant. Simple meaning for that is AI researchers often assume that computing power will stay the same. Okay, they thought we only have this much computing power, So we must make our AI smarter by adding human knowledge, means adding more rules only, right? In which case leveraging human would be the one of the only ways to improve performance. Simple mean, if your computer cannot become faster, their only way to improve AI is to let the humans manually teach it by writing rules, right? For example, instead of letting the AI to learn the patterns, programmers write rules. Okay, if ears are pointy, maybe cat. A broad position looks like this. You go chest move like this. So human knowledge replaces learning in this case, right? But over a slightly longer time than a typical research project, massively more computation inevitably becomes available. What does that mean? It's saying a research project may last 2-3 years. Okay. During that time or soon after, computers become much faster and cheaper. Now, the same AI algorithm can perform 100x or 1000x more computations, right? So, it learns much better. This means the manually written rules become less useful, right? Okay, so how many rules you can write in these 2-3 years of research? But the computation becomes, you cannot outperform this 1000x or 100x computation in that case, right? This means the manually written rules become less useful because it can perform more computations, right? And also it can learn more things because it can perform more computations, right? So simple example, imagine it's 2010, your computer can train a neural network for only 1 hour. So researchers think, okay, the computer is too weak, let's manually add more rules, okay. But in 2025, your computer is 1000x faster, right? The same learning algorithm can now train for billions of calculations and becomes far better than handwritten rule system. That's what it was saying. Okay, the author's main message, researchers often designed AI assuming computer is like fixed power, right? But they focused like, okay, more human knowledge is better AI, but history showed that computers power kept increasing. More computation means more computation leads us to general learning algorithm, right? And this algorithm also improve automatically, not the algorithm but the AI. It will improve the AI automatically and better AI we will get. So according to Sutton, betting on increasing computation and general learning algorithms turn out to be much better long-term strategy than relying on hand-created, crafted human knowledge, as we can see nowadays, right? Also, seeking improvement that makes a difference in the short term, researchers seek to leverage their human knowledge of the domain, but the only thing that matters in the long run is leveraging the computation. Right? These two need not run counter to each other, but in practice they tend to. Okay, let me do this also. This is the same thing, I think, what we already discussed, but okay, we will get this also. Can you explain this in simple language and in brief also, right? Seeking improvement that makes difference in short term. Okay, researchers seek to leverage their human knowledge of the domain. So simple meaning, researchers often wants quick improvements, right? So instead of waiting for better computers and more data, they use their own expertise. A chess expert adds chess strategy rules, a doctor adds medical rules, a language expert adds grammar rules, right? This gives faster short-term improvement, but the only thing that matters in the long run is the leveraging of computation. In the long run, using more computation, like more training data, more compute, beats manually adding human knowledge, right? So as computer becomes more powerful, general learning algorithms eventually perform better than handcrafted systems, right? These two need to run counter to each other, right? But in practice they tend to. So the simple, ideally you could use both, right? Human knowledge plus computation, so they don't have to conflict. But in reality, researchers usually spend time on one or the other, right? Often, adding human rules makes the system less general, okay, and harder to improve simply by scaling computation. Okay, so if we add more human rules, so it makes harder to system to improve and make it less general. It makes it less more specific. Okay, this is very important. If we add more human rules, very important line, right? Yeah. So if we are adding more human rules, the system becomes less general and harder to improve simply by scaling the computation for us, right? One line summary for us is like researchers often use human knowledge because it gives quick improvements, right? But history shows that investing in general learning, okay, like in computation methods that can use more computation leads to much bigger improvements over time. Also, one more thing, if we can we use both computation and human knowledge? Like, they don't have to conflict, it seems like, but in reality, researchers usually spend time on one or the other because often adding human rules make the system less general, okay, and harder to improve simply by scaling. Very important line. If we add more rules, the system becomes more specific and less general. Time spent on one is time not spent on others. Yeah, that's true. There are psychological commitments to investment in one approach or the other, and the human knowledge approach tends to complicate methods in ways that makes them less suited to taking advantage of general methods leveraging computation. There were many examples of AI researchers belated learning of this bitter lesson, and it is instructive to review some of the most prominent. Okay, so I think we covered that, but let me also pass through that here from here, right? Okay. So it's going sentence by sentence this time. Time spent on one is not time spent on the other. Simple meaning. So because researchers have limited time, if they spend time writing human rules, they are not spending that time improving learning algorithms or making better use of computation in that case, right? So there are psychological commitments to investment in one approach or the other. Simple meaning, people naturally become attached to the approach they have worked on for years, right? For example, a researcher who has spent 10 years writing expert rules may not want to admit that a simple learning algorithm is better, right? So if some researcher is writing code, right, and systems, designing systems for for decades, like let's say 1 or 2 decades, he's an expert in his field, or like you can example, cybersecurity expert, right? He has been handling systems, but a model, language model, right, which only trained on some data and used some computation, can find vulnerabilities in the system which he cannot find, right? Or in the system that expert has designed. The number one expert cannot find or the vulnerabilities in the system, but the simple AI model who only trained for few billion parameters and few days can find that, right? So he cannot, like, this is psychological bottleneck here, right? He is more attached, committed to that his approach only, right? He don't want to admit that okay, this model is better than me, right? The human knowledge approach tends to complicate methods in ways that make them less suited to take advantage of general methods leveraging computation. So human complicates the general method because it makes them more specific and less general. Simple meaning is adding lots of human made rules makes the AI system complex and specialized. Like specialized, right? So as computers become faster, these systems cannot easily improve just by using more computation. On the other hand, a simple general learning algorithm like a neural network can improve naturally by training on more data with more compute. Okay, so there were many examples of AI researchers related learning of this better lesson. Right, simple meaning, many AI researchers realized only after many years that they should have focused on general learning methods instead of handcrafted rules. This realization came late, like belated, right? Belated learning of this, right? So this realization came late, which is why Sutton calls it a bitter lesson. All right. Okay, and let's move further in the paper, or the we can say the in the article. In computer chess, the methods that defeated the world champion Kasparov in 1997 were based on massive deep search. At this time, this was looked upon with dismay by majority of computer chess researchers who had pursued methods that leverage human understanding of the spatial vastly more effective. Okay, these human knowledge-based chess researchers were not good losers. Okay, let me go with, it's a very simple, I think not technical, so we can take it in one go, right? Can you explain this in simple? Let me like it first. Okay, language and in brief. Okay, let's go. This is one of the in computer chess, Kasparov based on massive deep research, right? The simple meaning for this is the chess computer Deep Blue was there was a computer called Deep Blue defeated world champion Garry Kasparov in 1997. So it did not win because humans taught it lot of chess strategies, right? It won because it could search and evaluate millions of possible moves every second using powerful computers. Okay, so 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 here also computation is winning, right? In comparison to this is before AI, guys. This is before AI era, right? So here also computation is winning, like winning over the human knowledge, right? So it won because it could search and evaluate millions of possible moves. So we have fed this millions of possible moves every second, right? And then it can search like what is the best possible move in this scenario using powerful computers. Okay. So researchers pursued method that leverage human understanding of chess. So simple meaning is many researchers believed the best way to build a chess AI was to teach it human chess knowledge such as control the center, protect the king. So they expected this approach to win, right? But what happened? This approach won, like computation approach won, right? Okay. Then they expected okay like that, and a simpler search-based approach. Search-based approach proved vastly more effective. Only searching what search search is based on computation, right? So here search means computation, you can say. So computation won in this case also. So instead a much simpler idea worked better. Search millions of moves, evaluate each position, pick the best move. Because computers were very powerful, this approach beat the human rule approach. Right? These researchers were not good losers. Simple meaning, many researchers were unhappy because their approach lost the human rule approach, right? Instead of accepting the result, they criticized the winning method, right? They said brute force search. Simple meaning, they argued the computer only won because it checked millions of moves. This is just real intelligence. In the case, they were true also, right? Because this was not real intelligence in this case. They were just searching. from the database. If database is corrupted, then the computer would have lost, right? So, and human don't play chess this way. They were right in that sense also. In other words, they believe the victory didn't count because the machine wasn't thinking like a human. So the lesson Sutton wants to teach here, researchers focus on making AI think like humans, right? But history showed that using more computation, like searching millions of possibilities, worked much better. So the important lesson is the goal is not to make AI solve problems the same way humans do. The goal is to make AI solve problems effectively, even if it uses like a completely different method, which is computation or search or anything like that, right? It's a very interesting case. Like humans solve problems differently, but computers solve problems very differently. A similar pattern of research progress was seen in computer Go, only delayed by a further 20 years. Enormous initial effort went into avoiding search by taking advantage of human knowledge or of special features of the game. But all these effort proved irrelevant or worse. One search was applied effectively at scale. Also important was the use of learning by self-play to learn a value function, as it was in many other games and even chess. Although the learning did not play a big role in 1997 program that first beat the world champion, learning by self-play and learning in general is like search in that. Okay, let me go one by one. It's a very heavy context heavy, right? Okay, where is the first full stop here? Okay, let me go. Let me explain it in simple language and in brief. So it says, this paragraph says the same mistake happened again in game of Go, just 20 years later after that. I'll be back in a minute. Right, guys? So the similar pattern delayed, okay, by further 20 years here. Simple meaning here is after chess, researchers made the same mistake in Go, but about 20 years later, right, enormous initial effort went into avoiding search. Okay, so they designed a system that was avoiding search. In simple meaning, researchers thought searching all possible Go moves is impossible. So let's teach the AI human Go strategies, right? So teach the AI human Go strategies. Okay. They spent years adding human knowledge such as good opening patterns, common Go shapes, expert rules like that. Okay. They feared that. They tried avoid using large skill sets. Okay. All those efforts proved irrelevant or worse. Like later, when computers became much more powerful, AI systems like AlphaGo, right, used large scale search plus learning. This approach became much stronger than the handcrafted rules based system. Okay. As a result, many years of manually adding Go knowledge becomes mostly unnecessary. Okay. The main lesson here is researchers believe human Go knowledge will translate to better AI, right? But history showed more computation plus learning plus large scale search gives us much better AI, right? So Sutton's point is instead of spending years manually teaching AI the Go strategies, right? It was ultimately more effective to build a general learning system and let powerful computers learn and search on their own. Okay, let's go move ahead. The use of learning by self-play to learn a value function as it was in many other games and even in chess, although learning did not play a big role in 1997 program because that was search based, right? That first beat a world champion. Learning by self-play and learning in general is two most important classes of techniques for utilizing massive amounts of computation in AI research. Okay, in computer Go, as in computer chess, researchers' initial effort was directed towards utilizing human understanding, so that less search was needed, and only much later was much greater success had embracing search plus and learning. So I think it was summarized earlier also, but let me do it again for transparency and much. We don't get like. Can you explain this in simple language and in brief? So this program para is explaining why AlphaGo becomes so powerful and what the two most important AI techniques are. Okay. So learning by self-play. Simple meaning, instead of learning only from humans, AI played against itself millions of times. By playing and learning from its own games, it becomes stronger and stronger. For example, AI versus AI, millions of games, it learns much better strategies and become the expert. So learning is like search. Simple meaning, both search and learning requires a lot of computation, right? Search, try and evaluate many possible moves, and learning practice millions of times and improve. Okay. So both become better when you give them more computing power. Okay. Search and learning are the two most important classes of techniques. Simple meaning, according to Sutton, the two biggest ways to use to use powerful computers are search, like explore many possible solutions, learning improve automatically from data or experience. These are the two ways key tools behind modern AI. That's true also, because the search is like RAG and all, the memory. Learning is the models, right? So these two are key tools behind modern AI. That is true, right? A researcher's initial effort was simple meaning is like at first Go researchers spent years teaching the AI human God knowledge to reduce the need of search, like need of computation. Right? Later, they discovered that it worked much better to let the AI search many moves and learn by playing millions of games against itself. This approach produced much stronger AI. Okay, what? Wait. Now let's move forward. Okay, only few. But in speech recognition, there was an early competition sponsored by DARPA in 1970s. Entrants included a host of special methods, right, that took advantage of human knowledge, knowledge of words, of phonemes, phonemes, right, of the human vocal tract, etc. On the other side were newer methods that were more statistical in nature and did much more computation based on hidden Markov models (HMMs). Again, the statistical methods won out over the human knowledge-based methods. This led to a major change in all the natural language processing. Gradually, over decades, where statistics and computation came to dominate the field. Okay. The recent rise of deep learning in speech recognition is the most recent step in this consistent direction. Deep learning methods rely even less on human knowledge and use more computation. Together with learning in the huge training sets to produce dramatically better speech recognition system. As in the games, researchers always try to make systems that work the way researchers thought their own mind worked. They try to put that knowledge in their system, but it proved ultimately counterproductive and a colossal waste of researchers' time. Research when through Moore's law, massive computation became available, and a means was found to put it in a good use. Okay, in computer vision, oh, very so they're the same thing. So let's go one by one. I think it was simple as we understood the earlier part, right? So let's go this also. Here, can you explain this in simple ways and in brief? Right. Okay, this paragraph have another example for this middle lesson. This time in speech recognition, what happened is in 1970s DARPA. Okay. Oh, it's editable also, right? In 1970, DARPA organized a competition to build systems that could recognize human speech. Okay, there was a competition, right? Researchers followed two different approaches in that. First approach, human knowledge. Many researchers try to improve speech recognition by manually adding expert knowledge such as how words are pronounced, how phonemes speech sound work, right? How human vocal tract produces sound. Okay, The idea was if we teach the computer how humans speak, it will recognize better speech better. And second approach was uh, statistical methods, right? Another group used hidden Markov models, HMM. Okay, instead of manually teaching speech rules, they let the computer learn pattern from large amount of speech data, right? Using mathematics and probability. This speech also required much more computation, right? This approach, right? So main lesson here is there were two competing ideas. Human knowledge approach teach the computer speech rules, and one was statistical learning approach (FMMs) like hidden Markov models. Let the computer learn from data using computation. Right? Over time, the statistical computation-based approach proved much more successful and become foundation of modern speech recognition systems. Can you tell me in simple language and in brief how HMM works? So a hidden Markov model is a mathematical model that guesses the most likely hidden state from a sequence of observations. Okay, simple idea. When a person speaks, the computer hears only sound waves, right? So it cannot directly see which word or speech sound the speaker intended. So observed like visible sound signal, hidden actual word or phenom, right? The sound tries to infer the hidden word from the observed sound. Right? So suppose someone says hello, the computer receives a noisy sound signal like sound 1, sound 2, sound 3, sound 4. HMM asks which sequence of words or phenomena is most likely to have produced these sounds. It computes probabilities hello 95 like this. It chooses the most probable one. Output is hello. So why it is called hidden Markov model? Hidden is the actual words of phenomena are not directly visible. Like Markov, the next state mainly depends on the current state, not the entire past. Okay. Phoneme C. Probably moving to the next phoneme depends mostly on the current phoneme. Why were HMMs successful? Instead of writing thousands of scripts by hand, HMMs learned probabilities from large speech data sets, used computation to find the most likely word sequence, improved automatically as more data becomes available. Okay.
Machine learning.
Again, the statistical method won out over the human knowledge-based method. This led a major computation. Okay, let me go here also. Can you in this simple ways and in brief also? Alright, so this paragraph is how speech recognition evolved and reinforced the better lesson. Okay. So statistical method won in that competition. The competition was what? Japra or what? DARPA. Okay, DARPA. Statistical method. The method based on statistics statistics and learning from data perform much better than systems built using manually written speech rules. As a result, researchers gradually stopped relying on human knowledge and started relying on more data and computation. Okay, and deep learning took this even further. Deep learning uses very little handwritten human knowledge. Okay, huge amounts of training data, massive computation, as we know as of now, right? Because of this, it achieved much better speech recognition than older methods like HMM, right? The researchers' mistake. Many researchers believe AI should work the same way humans think, right? So they try to manually teach the AI human knowledge that about speech. Whoever, whoever still showed that this was not the best approach, right? The real winner, as computer became much more powerful, and thanks to the Moore's law, the doubling the transistors every 2 years, AI systems that learn from data and use large amount of computation became far more successful than systems built from human design rules, right? Many lessons researchers spent many years trying to make AI think like humans, but the biggest breakthrough came when they built general learning systems and let them learn from massive amounts of data using powerful computers instead of manually encoding human knowledge, right? That was it. And next, in computer vision, also I think some shift happened there, right? In computer vision, there has been a similar pattern. Early methods conceived of vision as searching of edges or generalized cylinders or in terms of shift features. But today, all this is discarded. Modern deep learning neural network uses only notion of convolution and certain kinds of invariances and perform much better in this case. Okay, let me go through this. So C and we have this. So V. Okay. This paragraph explains that computer vision followed the same pattern as chess, Go, and speech recognition. Okay. Early computer vision researchers believed that they had to manually tell the computer what to look for, right? They designed features such as look for edges, detect object boundaries, right? And generalized cylinders like represent objects using simple 3D shapes, right? And shift features and design features to identify important points in a image, right? So the idea was, let's teach the computer how humans recognize objects. And the modern computer vision, today deep learning takes a different approach. Instead of manually designing features, a convolutional neural network CNN learns the useful features automatically from millions of images, right? The only human designed idea are were general concepts such as convolution, looking at a small part of an image to find patterns, right? And invariance, recognizing an object even if it moves, rotates slightly or changes in size. Everything else is learned from data. right? Main lesson: earlier researchers spent years designing handcrafted images, features like edges and shift. Modern, like, okay, very understandable also. So this is a big lesson for us. As a field, we still have not thoroughly learned it, and we are continuing to make the same kind of mistakes to see this and if actually resist it, right? We have to understand the appeal of these mistakes. We have to learn the bitter lesson that building and how we think does not work in the long run. Right? So the building in how we think, okay, does not work in the long run. The bitter lesson is based on the historical observations that one is AI researchers have often tried to build knowledge into their agents. Two, this always helps in the short term and is personally satisfying to the researchers. But three, in the long run, it plateaus and even inhibits further progress. Okay, but and four, breakthroughs progress eventually arrives by an opposing approach based on the scaling computation by search and learning. Eventual success is tinged with bitterness and often incompletely uh, digested because it is success over a favored, so human-centering approach. One thing that should be learned from the bitter lesson is the great power of general purpose methods, or methods that continue to scale with increased computation even as the available computation becomes very great. The two methods that seem to scale arbitrarily is the way search and learning. So I think it was understandable as we go, but we will still go to ChatGPT and ask for simple language explanation. So can you explain this in simple language and in brief also? Because we already understand this. Right. So this paragraph summarizes the main message of bitter. We keep repeating the same mistake. Even today, AI researchers sometimes try to improve AI by adding human knowledge and handcrafted rules instead of building systems that can learn by themselves. Right? So, if we are building agents in today and age, we write like agents some rules, right? But those rules can be learned also, right? Instead of writing them by hand, right? We keep repeating the same mistake even today. Okay, why do we make this mistake? Because it feels natural to think. If I know how humans solve these problems, I will teach the AI the same way. This often gives quick improvements, so researchers feel their approach is correct. Why it is called the better lesson? History has repeatedly shown that researchers add human knowledge to AI. It works well in the short term, but after some time, the improvement stops being plateaus, okay, and makes further progress harder. Plateaus. Stops means plateaus. Improvement plateaus, and later a general learning method that uses more computation. Later a general, okay, search and learning surpasses the human design approach. Why it is better? Because it is called better because researchers often spend years building systems based on human ideas, right? Only to discover that a simpler system that learns from data and uses massive computation performs much better. This can be disappointing because the winning approach is not based on human thinking, but on letting the computer learn from itself, right? Okay, let's go for next paragraph. One thing that should be learned from the better lesson is the great power of general purpose methods, or the methods that continue to scale with increased computation even at the available computation becomes very great. The not on the scaled increased computation, even at the available computation becomes very great. The two methods that seem to scale arbitrarily is the search and learning. It's very important. Let me guide it through here. Okay, so can you explain this in simple language, right? And in brief also, right? So this paragraph explains the main advantage from better lesson. What should we learn? We should build general purpose AI methods instead of task specific systems. A general purpose method is one that works for many different problems and becomes better when we provide more computation, more data, and more training time. Okay, so we should go for general purpose methods, right? Build does scale with increased computation mean? So it means that as computers become faster and more powerful, some algorithms keeps improving, right? Same algorithm. For example, train for 1 hour is like good performance, but train for 100 hours on a bigger GPU, better performance. Train on millions more examples, even better performance, right? So algorithm does not need to be redesigned. It simply benefits from more computation, right? Like gradient descent here. Algorithm is same, but if we give it more data and more compute, then it perform better, right? Which methods scale the best? According to the solution Sutton, two methods continue to improve as more computation becomes available. One is search, explore many more possible solutions, chase or learning, learn better way from more data and experience, okay, like deep learning. Search and learning. These methods keep getting stronger as computation increases. Okay, now let's go for last paragraph. The second general point to be done from the better lesson is that the actual contents of minds are tremendously, irredeemably complex. Okay. We should stop trying to find simple ways to think about the contents of mind, such as simple ways to think about space, object, multiple agents, or symmetries. Right? All these are part of arbitrary, intrinsically complex outside world. They are not what should be built in, right? As their complexity is endless, instead of we should build in only the meta methods that can capture this arbitrary complexity. Essential to these methods is that they can find good approximations, but the search for them should be by our methods, not by us. We want agents that can discover like we can, not which contain what we have discovered. Building in our discoveries only makes it harder to see how discovering process can be done. It's very important. Last paragraph. Can you explain this in simple language and in detail? Because it's a new thing, right? Okay, let's read this paragraph out also. So this paragraph explains the second major lesson from the better lesson. It says that we should teach AI how to learn, not teach it everything we know. Right? So actual content of minds are tremendously or irredeemably complex. That's true. Everything humans know about the world is extremely complicated. Examples include recognizing faces, understanding language, driving a car, playing chess, understanding emotions, navigating a city. There are millions of tiny rules and patterns involved. Okay, the world is simply too complex to write all these rules by hand. Right? We should stop trying to find simple ways to think about the contents of mind. Okay, simple meaning is researchers often try to simplify human intelligence by saying think like this. Objects work this way. Space should be represented like this. Humans reasons like this. Okay. Sutton says this is wrong approach. Human intelligence is too complicated to be captured by a few handwritten ideas. Space, objects, multiple agents, symmetries. These are examples of concepts researchers try to manually build into AI. Right? For example, teach AI what an object is. Teach AI how people interact. Teach it symmetry rules. Teach it how humans reason. Sutton argues that there are too many exceptions and details. No matter how many rules we write, the real world is always more complicated. That's true. Instead, we should try build only the meta methods. This is the most important sentence. Meta methods. A meta method is a method of learning, right? Not the learning. Learning is not the method. Method of learning is the meta method, right? Not a collection of knowledge. Instead of giving the AI answers, teach it how to find the answer. Right? For example, instead of saying cats have whiskers and pointy ears, so build a learning algorithm that can discover this automatically from millions of images. Right? We don't give answers. Model find answers itself. They can find good approximations. AI doesn't need to understand the world perfectly. It only needs to learn a model that is good enough to solve the task. For example, ChatGPT does not memorize every English grammar rule. Instead, it learns statistical pattern from enormous amount of text. Those learned patterns are good approximations, right? The search for them should be by our methods, not by us. Okay. This means researchers should not manually discover every rule. Instead, they should build algorithms that discover those rules automatically. So wrong approach. Human writing rules. We want AI agents that can discover like we can. This is a Sutton main message. We do not want AI that simply stores everything humans already know. We want AI that can make new discoveries. Just like humans can. For example, scientists discover gravity. Future AI should also be able to discover new scientific laws instead of only repeating human knowledge. Building in our discoveries only makes it harder. If we fill AI with human knowledge, it becomes harder to understand how learning itself works. Instead, if we build a general learning system, if it can discover not only what humans already know, but also things humans have never discovered. Main takeaway is the world is far too complex for humans to manually program all the rules into AI. Instead of building AI that okay. In other words, don't teach AI every answer. Teach it how to discover answers. That is the core idea. Okay. Can we find any contradictions, objections in against this article? tell me in simple language and in brief also, right? We can go for think what, deep research, visualize, GitHub, Canva, wow, what, create me web search, refresh, get a detailed report, no, visualize, no, what? You need to think, thinking, right? Thinking. There are some strong objections, so not the clean contradiction. Okay, in the human knowledge helps when data is small. If you only have 10 under, okay, that's compute is not always unlimited. Article says computers keeps growing, but in real life it is essential for many teams. An built method can beat a huge training run. Okay. Some problems need a strong structure. In medicine, physics, robotics, built-in rules can make systems safer and more reliable. So just learning everything is not always best. Hybrid methods often win. Best system are often mixed. Okay. The main objection is better lesson is more often true in the long run, but human knowledge still matters. The high cost replicated highly structured problems. Okay. So thank you so much, guys, for watching and be with me. I hope you were able to understand this, right? And I understood it. And yeah, let's go through the